Hi, my name is Hannah Spiro, and I'm one of your TAs for Water in the West. Today, I will be walking you through a basic HEC RAS model or HEC RAS model, and this is going to be a module about why do we use numerical models and how do we model two-dimensional versus one-dimensional flows, such as rivers. Now, what is a hydraulic model and what is hydraulic modeling? Well, to begin with, you want to get some information about a river, and there are several options for modeling a river. We could do these calculations by hand, which would mean it's not spatially dependent, and this was done in the 1950s to 1970s, and it's called level pool routing. But today, most people, such as engineers, biologists, and geologists, use 1D models or 2D models to represent flow through a channel. So hydraulic means denoting, relating to, or operating a liquid moving in a confined space under pressure. So all liquid on the earth is under pressure, and we are trying to calculate where it's moving, how it's moving. Modeling. So it's the act of representing something, usually on a smaller scale. So we can represent it in 1D, in 2D. We will not get into 3D, but that is what hydraulic modeling is. And for all purposes for this assignment, we will be using HEC RAS 5.7 version. And this is a software that's used to model water flowing through rivers, compute water surface profiles, including the analysis of where water will encroach in a flood event, such as FEMA, or you can think of even a Hurricane Sandy and the water moving up the rivers. And this is the most commonly used tool in the river hydraulic sector in the United States, which is why we're focusing on it. So for section 2, what is HEC RAS? We will be talking about the program, which allows engineers to compare existing conditions in the real world to proposed conditions that you can model. So some of the general functions can include a bridge hydraulic analysis to assist with bridge designs. How low should the bridge be? How can we save money economically, but also make sure it's safe? It's also used in conducting floodplain analyses, river hydraulics, flood mitigations. It's used by FEMA often, and then I use it for dam failure modeling, which is another application by the U.S. Army Corps of Engineers as well. So as an example with what is HEC RAS or what is HEC RAS, we have here in Colorado on the left, we can see this is a river that's moving through this profile, and then the lines that are crossing it perpendicular are cross sections. So this is a 1D model of what we can see on the right, which is completed post-flood roadway repairs at County Road 29 in Larimer County. This is near the Loveland Water Treatment Plant, if you've been down to Colorado. But the HEC RAS model was used to design the repairs. So this is one example of usage and importance. So here we have a figure, or two different figures, where these images are illustrating the difference between 1D and 2D modeling. So in both 1D and 2D models, the vertical direction z is assumed to be constant, which means it goes to 0 and we don't have to model it. But while water levels in the y direction are assumed to be constant in the 1D model as well, which is why it's simpler, in 2D models, we're modeling the full flow velocity, water depths, and widths, which can vary across channels in 2D models because there's variability between the x and the y direction. So here is an example of a HEC RAS project recently performed where on the left we can see there is a RAS mapper outline here of this flood domain, and this is in 2D, so we have to use topography for modeling in 2D. And then on the right, this is the one-dimensional version with all of these cross sections in green and the river line in red. And so while 1D models solve the St. Bernard equations, which are the equations for flow, you might have heard them referenced as the shallow water equations, a 2D model will solve them in 2 dimensions. So the simplification for 1D means it runs the model a lot faster, it can give you data a lot quicker, but the trade-off is it is simpler, so there are assumptions involved. The user can force the program to use 2D equations for a 1D model, but we will not get into that. until we hit the mathematics section. So I wanted to give you guys a graphic to demonstrate a 2D model domain versus a 1D model domain. So we can see here there's a 2D model domain with a mesh, and this is an elevation-based mesh, which is why it has these rainbow colors. Each is linked to an elevation gradient. And then this is our river down in blue with these points, which are nodes. It's just places where they're going to compute the equations. And then there are the cross sections in red, which are the 1D cross sections. So this is giving you a visual of the 1D versus 2D model, which you can use. And then just to go a little bit more in depth into the differences between 1D and 2D hydraulic models, there are data structure differences, such as the terrain data. So you'll go out and you'll survey a river, and then for 1D, you'll use station elevation points for the cross sections. So where was the water level? Where were the banks? Were there any trees and foliage near? But for the 2D model, you need to use spatial data, such as LiDAR or a downloaded DEM, or digital elevation model. And here they talk about a DTM, which is a digital terrain model, which is similar because you're modeling the flow of water over a differing y direction. So we have to have that. The terrain discretization is different, cross sections versus a 2D mesh, but both are able to model bridges, model culverts, inline structures with gates, and many other things. So now you might be wondering, well, when are we going to use 1D versus 2D, since we've gone over some of the components of both of them? So here I've outlined when we would use a 1D model. So in terms of time, imagining we're in the working environment, we might need to output a model within a day. So we could use a 1D model, which runs significantly faster, and we could output data quickly. We also could output data if we don't have great terrain data. We don't have LiDAR flights or drone flights in this area. It's remote. We could use a 1D model for an approximation. And then lastly, if streams or channels have unidirectional flow, where they flow maybe north to south or east to west, they have defined overbanks, so canals, mountain streams. These are all options where you could use a 1D model and it would have good approximations based on previous research. But on the other hand, if you are excited by the images that a 2D model could produce and you are wondering when you could use those, urban areas are important. So on the right, this is an image of a velocity HEC RAS model in Boise, Idaho. You can see the terrain data in the background with the city. And then the velocity, the blue is the highest velocity to the red, which is the slowest. So there's the outline of part of the Boise River and then the flood escaping from the river because it's so substantial. We also use a 2D model in wide floodplains, an area where flow spreads, such as an alluvial fan, which you might have learned about in geomorphology, in dam break studies, which is my research, and then areas where there's narrow bridges. So we could think of maybe the Friendship Bridge on campus, because that can cause significant expansion and contraction. And so we can represent it more accurately with a 2D model, so it's worth taking the extra time. I also want to note that with 1D and 2D hydraulic models, the advances in computation and computers and the efficiency have meant that you can now perform a 2D model almost as quickly as a 1D model. So the time component of this is not as necessary in making a decision. So now I'm going to walk you through what the HEC RAS GUI looks like, or graphical user interface, and how a project is organized when you're using this software. So to begin with, you start with a project. So a project is going to be saved within the GUI, which we can see here on the screen, where the red circles are. So you'll have to name the project. Giving it a description is important, so you'll know how to search things and you'll know what you're modeling. Within the project, then, we use RASmapper to begin with. If we're starting with a 2D domain, we want to have a 2D model. So here you'll have to insert topography, which we'll talk about later with spatial data. You'll model 2D flow areas on top of it, and then you'll also need to determine what projection it is in. So like Leho talked about with QGIS, sometimes you get data and it's in different forms, like it's referenced to the whole Earth or it's referenced to a local datum. And you'll learn more about this in ArcGIS, but we also need to specify the projection, so we'll model the flow accurately on top of the topography. Next, in a project, there are geometries that need to be created. So you might be using an existing geometry or a proposed. So in this case, existing would be perhaps there is a weir that's located on the edge of a river or a bridge, and you are drawing or coding in that existing geometry. On the other hand, maybe this is a study to decide, should we dam this river or should we not? So you might be proposing a dam geometry and comparing it to the existing geometry. The geometry file is in red, and then we also can get to it by going to Edit and then Geometry. Once we have established a geometry and worked in RAS Mapper to have our topography, then we can either model in a steady flow state or in an unsteady flow state. And we'll go more into that with the mathematics. But those are our two options for all purposes of today. Let's just say we're modeling in an unsteady flow. So then we would have an unsteady flow data box that we would need to populate, and we'd also need to have a plan. So our plan would have initial conditions and it'd have runtime parameters. And this is where the plan box is located. It's also under the Run button. And lastly, we'll want to visualize our results. So then here in yellow, we can go back to RAS Mapper, and it's quite interactive. It's based on the Esri projects like ArcMap or ArcGIS or QGIS. And so then we can use that to visualize our data either over our topography or over Google Earth imagery or maps. And this is where our results will be, back into the GIS tools or the RAS Mapper button. So now I'm just going to quickly go over the menu bar information. At the top of the main HEC RAS window, there's the menu bar. This contains the commands for all primary functions. So the program file is used for Windows file management. Edit is used for entering and editing data. View is used for viewing model data and results. Run is used to perform hydraulic calculations. Options can determine what equations you're using or program options. GIS tools links to the RAS Mapper tool. And then if you have other questions, you can use the help button, which will link you to the HEC RAS manual or hyperlinks, and you can search your question. Then at the top of the main HEC RAS window, this is the menu bar, and it's also located below in red, but this will give you easy access or one-click access to the most frequently used commands. And the more you use HEC RAS, the more familiar you will become with those. And then third here, these are the boxes, which we've already talked about a bit, where you can enter the name of all of your files, so you'll be able to see which files you're using for what runs. So there are 5 steps in developing a hydraulic model. So we start with our new project. Second, we use RAS Mapper to enter geometric data, and we also go into the geometry editor, depending on what we are modeling. Then we will enter flow data such as cross sections, or in 2D models, we'll have to enter initial and existing conditions. 4, then we would create plans to perform the hydraulic calculations. And 5, we would want to view and print our results. So pause this really quick and think about what might we be missing. So there's actually 6 steps when you're developing a hydraulic model, and that's because the first time you run a model, it might not be exactly what you want. It might not be accurate. There could be things that are incorrect. You might receive errors. And so modeling involves iterating, which you've learned probably with Excel so far, but we want to repeat steps 1 through 5 until we get a satisfactory solution, which could mean a low error percentage or a low uncertainty in the value. So there are several physical laws that govern the flow of water. So there's the conservation of mass, which we call the continuity equation. There's the principle of the conservation of momentum. And these 2 laws are expressed mathematically in the form of partial differential equations, which we can call the continuity and momentum equations moving forward. But there are some forces that affect these equations or that come up in the form of variables in this equation that are important. So for example, gravitational forces or pressure forces There's friction forces, which we call the Manning's roughness coefficient, or the Manning's N. This is also known as the drag coefficient. There's the water surface slope. And then depending on how big your domain is, domain meaning wherever you're modeling, there could be Coriolis forcing, which is the curvature of the surface of the Earth and how it might be affecting your solution. For example, I'm modeling a 70 mile by 70 model domain, and this is small enough where we don't see Coriolis forcing affecting it. But if you were modeling the whole United States or the whole state of Idaho, you likely would need to use an approximation for the Coriolis forcing. So here is a MATLAB visualization of the Navier-Stokes equations, or the shallow water equations, propagating in an open system. So we'll talk about this in a mathematical sense. So to begin with, when we're modeling an open channel flow, we use the same finite equations, such as the continuity equation and the momentum equation. So in this continuity equation, we are modeling the change in flow, which is this dq value, and the change in area with respect to time. And we're setting that equal to 0 because we made several assumptions. For the momentum equation, here we're still looking at the change in flow with respect to time. We're using area approximations, but here we're looking at the change of flow with respect to area. We're adding in a gravity term. We're also looking at the y versus the x direction. And once again, it's set equal to 0 because of an assumption that the change in storage, our water that's in the beginning of the simulation is the water that's in the end of the simulation. So we're conserving our water or conserving our mass. And so in these equations are the simpler equations, so they aren't partial differential equations quite. And so this is one-dimensional. We're talking about hydrostatic pressure prevailing, vertical accelerations are negligible. So it's not moving up or down necessarily, just horizontal. The streamline curvature is small. The bottom slope of the channel is also small. So these are approximations that have to be made, and then we have to meet these assumptions. And then we're using the Manning's equation to describe resistance effects, or the drag coefficient, or the roughness. And so here we can see a plane view, or this would be map view, of a flow entering what we call a control volume. And there's an inflow, there's a lateral inflow, and we can see there's many different parameters we're having to think about when we're modeling open channel flow, even in just one dimension. And so if you're really interested in this, I would encourage you to check out a engineering course in it. There are several, especially one that's coming up with Dr. Kevin Roche, who studies open channel flow dynamics on many scales. And so this is the cross-sectional view of our application that we just saw here in map view, where we have flow. This is going downstream. We are assuming a slope, which is theta. This is all referenced to some datum, which has to do with what projection we're in or how far above the water table it is, whatever datum you decide. Here is the water table. This is the arrow. That's what it means. And then we're also looking at the energy. There's gravity terms. There's a lot of different terms in here. So all of those terms that we saw on this other page right here where we were applying them, those are all evident within our application, such as this gravity forcing, friction forcing. Is the water contracting or expanding? It's technically incompressible. And then are there wind forces? So everything you can think about, we can add a term in to mathematically describe it. But our primary focus for this lab will be on Manning's equation. So breaking down this equation, we can see that Q is the flow rate. So this is expressed in cubic feet per second, or CFS. And this equation above is expressing flow, because both sides of the equation have been multiplied by the flow area, which is A. The 1.49 is a units conversion factor, because we are modeling in terms of the American US customary units instead of in meters or SI units. The N is the Manning's roughness factor. So this is a unitless value that represents the roughness factor of the conduit. And then the A is the cross-sectional area of the flow, which is expressed in square feet. The R is the hydraulic radius, which is expressed in feet. So this is used to account for the channel geometry. So as the radius changes, the wetted perimeter of flow will also change. And then there is the S value, which is the slope of the energy gradient. which is just expressed as a raw slope, so we don't have to deal in percentages, so it's in feet per feet. And it's also common to substitute the channel slope for the energy slope. So wrapping up this video, let's talk about Section 7, applications of why to use the hydraulic model, and then Section 8 will cover spatial data. So there are many reasons why we would use a hydraulic model. It informs economic factors, risk factors, flooding estimations. A lot of what FEMA does uses hydraulic modeling of different sorts. We also use it in academia and in research. And today the purpose is largely to understand the equations by applying them to real life and seeing how you might change different variables, and the result or the flow of the river might also change. In your very brief overview for spatial data and hydrology, because we'll be using that in RAS Mapper. So it's evolved over the past decade. We're not just using satellite data, we also can use data from drones called drone photogrammetry. We can use small airplane flights to collect LiDAR data. And having these geospatially correct hydraulic models have significant benefits over non-spatially correct models, or even 1D models which don't have spatial benefits. Model data can be interactive with other softwares that utilize the spatially correct data, such as QGIS, ArcGIS, ArcMap. And for me, I display all my results on Google Earth. And results can be presented in meaningful ways. So you can think if you're having to approach the government and lobby for inputting dams, taking away dams, you're modeling a river, and maybe you think it might flood your property. These results can be presented in meaningful ways where anyone is able to access the material and see what the results of flooding would be. And because of the spatial data evolution over time, it really has allowed for us to model in 2D as fast as 1D, which we talked about before. And it's paving the way for, hopefully in the next 10 years, we could even model in 3D and it would be applicable. So I have two quick examples. So first there's TINs. So TINs stand for triangular irregular networks. And we don't need to memorize that term, but they're often used in the ArcGIS community to represent a surface morphology in high detail. And that's because it uses a triangulating set of vertices or points, and it's raster sized, but based on vector digital geographical data. And so what all those words mean is this is a very high resolution image that you could use in a presentation or in a memo to a boss or to a government. And you can also export HEC RAS river flow data and overlay it on these TINs, so you can have meaningful representations of your work. Another example is, this is my Teton Dam flow site with the reservoir up in the northeast and flowing downstream to the southwest. But I had to use ASCII data from online. So you download data and sometimes you don't have a choice with what form it's in. And I had to change this data into a raster, which involved using QGIS, kind of like Leho talked about last week. So I had to change the format, and then I am now able to have my 2D model run on top of it. But without having that knowledge of how to use spatial data and run, I wouldn't be able to get model results that would show things like this, where we have the elevation gradient in red to orange. We have the reservoir here, the Teton Dam, and then we have overlaid on here is the 2D mesh. So really through spatial data, we've been able to evolve our capabilities. And so here are our 4 takeaways. So the first one is all models are wrong, but some are useful, which also ties back into our 6th step where we have to repeat and iterate through steps 1 through 5 in order to create a model that is valid. The second takeaway is there are physical laws that govern flow based on the conservation of energy, the conservation of mass, and the conservation of momentum. And so we can use these laws to create simple models or very complex models depending on the amount of variables we want to use. The third takeaway is that using a hydraulic model is important because it can allow us to understand variables in the equations. It can allow us to propose solutions to issues or to model current issues and see what might be other sorts of solutions, such as existing versus proposed geometry. And then finally, a big reason why we can use HEC RAS 2D in this lab instead of 1D is because of the recent advances in computing or higher resolution spatial data. So I'll be showing you at the minimum a 2D model with flow, And then in the lab, we can either apply 1D or 2D models with our given data and draw some conclusions. So with that, I'd like to say thank you for watching the whole video, and I will look forward to teaching you more about HEC RAS and modeling in 2D and 1D flow states.